Yeah, thanks for the introduction. So, very good morning, and all. So, I'll be talking about non-destructive measurement of microcoating thickness using step frequency photoacoustic sensing technique. So far we have listened to all like fabrication steps. So it is definitely not in that context. So, firstly, before starting, like the coil coating industries, like are the like these you can see these steel rolls that are huge kilometer rolls that are coated by paints and primers and different layers, and that are used in different application, multiple applications. So there are some problem that challenges with this industries are facing, and they need a definite solution because it has a huge market and the CAGR growth of approximately USD 8 billion is expected by 2025. So on behalf of all my co-authors, I Abhijeet Gorey from Embedded Devices and Intelligence System Group, TCS Research, Kolkata, welcomes you to this talk. So before proceeding, sorry. Yeah. So the points of discussion will be like, what is the exact problem statement that are faced, the challenges faced by the industry, the state of the art, proposed solution, the system architecture, results and potential impacts of this method. So the problem statement, like before going, the major markets for this coil coating industries are like construction, industrial, consumer, and automotive. Only this much of market is approximately expected to go to 6 billion USD by 2025, which is approximately 4 right now. So challenges that the production to demand is not met. The reason being the high rejection rate of the coated coils because of the different incorrect parameters, that is the thickness of the coating layer, the color deviation, or the gloss deviation. These three parameters are very critical apart from others definitely. The coating lines, when during the paint spraying, the coating lines move at a speed of 50 to 100 meters per minute. And after, in the present scenario, after every 5 kilometers, the sample is destructively taken out. It has taken to some lab-based settings where using different instruments, these all three parameters are measured. So approximately 20 to 30 minutes just go in measuring and giving the information to the controller or the operator of this coating line. So due to that, if you can think that 5 to 100 meters per minute, if it is like 5 kilometers, if they are testing and the report is going, if it is wrong, then the entire steel sheet or the metallic sheet, that much of primer, that much of paint, that's a huge loss. Okay, so that's why the industry demands that if we can significantly reduce the quality check time and frequent monitoring so that it can be informed to the operator so that he can control the ender itself. So we have worked on this problem. So the state of the art like shows that for coating thickness measurement, approximately 5 to 15 micrometers of thickness has to be measured very accurately at accuracy of 2 micrometers. So presently it is done with the help of cross-sectional microscopy. Color meter is used for color deviation. Gloss meter is used for gloss deviation with a delta E of 1 and 2 to 4 gloss units. So time required 20 to 30 minutes, and approximate cost of all three instruments is 7 to 10K USD. So if they want a non-invasive, non-destructive measurement for estimating all these three parameters, so if they can connect something to the coating line itself, then it can have a frequent measurement of these three parameters. So the demand is to have a single sensing unit with a maximum time of 2 minutes at the cost of USD approximately 1K or max 2K. So we have worked towards this solution using a photoacoustic sensing technique. Photoacoustic, we are like aware that mostly this sensing technique is used for a biomedical application due to its obvious advantages and benefits, but it has multiple industrial applications. People have worked in different domains, but somehow commercially there is like biomedical instruments are available, but no industrial instrument. So before going the brief of that, like for optics, like photo, we can have a color and gloss measurement, and acoustic, we can have a thickness measurement. So we thought why we can not use the combined technique as this thing to give the color, gloss, and thickness using a single method. So using this sensing technique, we can it can be a time efficient, a single sensing solution, as well as the cost effective solution if we are not using the pulse laser course, and using a compact laser that we will discuss. So in this, what happens is the modulated CW laser diodes go and hit the sample. The sample absorbs the heat of the laser radiation, and due to increase in temperature and pressure, it expands. And while relaxing back, it releases the gained energy in a form of non-radiative, that is acoustic wave, which is sensed by the sensor, and data acquisition and to computer, the processing is done. So the basic core principle is increase in temperature of the sample due to absorption of laser, increase in pressure, thermoacoustic expansion, and acoustic wave generation. So this is the basic physics principle that is used in photoacoustic. And in this study, we have used Rosencwaig-Gersho model, RG model, for estimating the micro thickness from the photoacoustic data. And this is the proposed sensing architecture, I would say, for this solution. Okay, and we are also working with some partner in the industries with this. So modulated CW laser diode can go to and hit to the coating sample. At the same time, the laser interferometer, which can act as a acoustic sensor, that is ultrasound sensor, and a photodiode to get the specular reflection from that to estimate the gloss. So this data can be used with the processing pipeline, AI interface if needed, and that's how this the complete sensor can be a non-invasive, non-contact, and non-destructive to sense all the three parameters at the same time in a very short interval of time. So in this paper, proposed paper, we have used right now, since we are like into development of this, we have used the ultrasound sensor that is in contact with the sample, and laser coming, hitting the sample, and this resonance spectra is captured, then used with the RG model and the calibration curve to estimate the coating thickness, color, and deviation, and the gloss measurement. So the basic, again, the physics equation, that is the diffusion thickness is inversely proportional to the square root of the frequency. That is the reason we have used the swept frequency to have the calibration response. So as the you can see that the diffusion thickness, that is the thickness of the coating, is increasing, so the frequency is reducing by the square root times. So this is the lab-based POC what we have done, and now already we have moved further with this. So coming to the results, so for result, we have for calibration, we have used 4 circular samples on which the paint is coated, and you can see there is a small dissection is made for a micro coating thickness that acts as a ground truth, and this is placed under the microscope to get the thickness. So these are the coating thicknesses in micrometers for different samples, and this was the photoacoustic response that is captured. So you can see for green 5, as the thickness is increasing, the sweep frequency is shifting leftwards. That is as per the RC model. So this, using this particular graph, we have developed the calibration curve of PA resonance frequency versus the coating thickness. And using this equation, the constants A and B are determined. So as and further for testing, we have used this randomly, random thickness samples. Again, with micro coating thickness, we have tested it for matching the results. And we realized that the PA measured thickness and actual thickness deviate less than 5%. So we are very close, moving towards the actual solution where the 2 micrometer thickness is demanded from the industrial side. And more and more, the data we train, definitely more accuracy we can get it. So that is for this. We have just developed a GUI inspecting coating layer with just one click, where the user or the operator can select the substrate, the primer type, and the color, and based on that, we can immediately get the data within a flash of 30 or 40 seconds. That the primer thickness is this, top coat thickness, what is the color, deviation in the lab values. If they want, they can get it, and the gloss unit. So all these parameters they can give a very short span of time. The potential impact of this particular study could be firstly, it can have a single setup, a compact setup that can be kept on the coating line itself. So online inspection of parameters is possible. Further, the rejection rate, that is the most critical and important for the coating industries. The rejection rate can be reduced, because as soon as they get to know that something is deviating, so operator can immediately control that part. Apart from that, it can also work for a non-contact surface profilometry method. And paint quality for different substrates we have tried. So it is working fine. For still few substrates, we have a challenge that we will work and overcome. So inspection can be carried out in real-time production environment, so that it can reduce the cost and time consumption. The future scope, like we are developing, or indeed some lab-based methods we have already done. So for optical interferometry, so all optical PA probe, it can be like a all optical photoacoustic, where the acoustic sensor will again a laser interferometer to sense its vibration. So that could be developed and installed with the coating lines, and technique can be used with different substrates. And in order to increase the accuracy or precision, I would say we are developing some simulation models, so that the training can be done with simulation and actual data can be tested on the real time scenarios. So yeah, that's also. Thank you very much for the queries discussion. You can always write and you can have it. Thank you.